So let's consider example number 1 for potential flow basics. In this example, let's consider we have a two-dimensional flow, a 2D flow that has a velocity potential given by this. Remember, when we say we have a potential, we are saying that it is possible that your velocity is equal to this. Okay, we can find your velocity like this. Okay, so the couple of questions for this. The first question is the fluid rotational? Well, you can go ahead and you could evaluate this, right? We know that this has to be 0 for an irrotational flow. And we also know that this is equal to the potential of this, right? But the way we derived it was from the fact that just the fact that you have a potential flow, just because you have a potential flow, it means that the fluid is irrotational. Otherwise, you would not have one. Okay, so it is rotational, irrotational, because phi exists. Okay, if it was the other way around, if phi did not exist, it would be rotational. Okay? This is understand the basics of how the potential flows work. Secondly, what is the velocity field? To find the velocity field, this is straightforward because the velocity field is equal to the gradient of phi. Now, in cylindrical coordinates, we have this e theta r partial of phi theta plus ez partial of phi respect to z. And you can see I interchange this all the time between theta and x because it really depends on the axis that you're working on. Okay, and different textbooks use different notations, so you have to get used to kind of seeing that. In this problem, you know this is 0 because your potential flow was equal to r sine of theta plus theta. Okay, so this goes to 0. It's not a function of that. So then you have ER respect to r. This gives you sine of theta plus E theta over r. Respect to theta, this gives you 1. This gives you cosine. So this gives you r cosine of theta plus 1. So your expression then, your velocity field is sine of theta ER plus cosine of theta plus 1 over r E theta. And then note that this is your UR, this is your U theta. Okay? Now the next question you asked for, what are the stream functions? So before we find the stream functions, we have to make sure the continuity equation is satisfied, right? So we want to ensure that this is actually equal to 0, and it should because the potential exists. Remember, this came from the fact that this is equal to this. When I'm telling you that the flow has a potential, so this continuity equation is automatically satisfied. Okay, so partial of r sine of theta plus 1 over r cosine of theta plus 1 over r partial of r. Okay, then this gives you sine of r over r minus sine of theta over r. This gives you 0. So the flow is incompressible. Okay, since the flow is compressible, alpha can be 1, and I can apply all my other equations. Okay, so I really want to find my stream functions. And to find your stream functions, remember we gave in the class notes the following. So since the flow is 2D, I know that one of my stream functions is equal to z, because this is all a function of r and theta. The other one has to be in the opposite direction, the direction that my flow, the other perpendicular to where my flow is moving. Okay, so this is automatic. So I know this is one of my flows, stream functions. I need to find the other one. So what I can do is I can use 1 over r partial of psi 1 over theta, and I also know u theta is equal to minus partial of psi of r, and you can go to your lecture notes and you can find that. So partial of psi respect to theta is going to be r sine of theta. Partial of psi respect to r would be minus cosine of theta minus 1 over r. So if I integrate this respect to theta, you can find that this is minus r cosine of theta plus a function in r. And if I integrate this respect to r, I find that this is equal to minus r cosine of theta minus natural log of r plus g of theta. Okay, so if I compare these two equations now, you can see I have this, okay, on both sides. I have r on both sides. And he's asking for another function of theta. I don't have one here. So what I could do is I can set this equal to 0, and I have found my stream function number, the first stream function. That would be minus r cosine of theta minus natural log of r. This is stream function number 1. And then psi 2 will be z, stream function number 2. Okay? So now the question is, calculate the circulation around this circle, r equal to a. So if I want to calculate this circulation, we know how I want to use the line integral. Okay, so r is equal to a. So we know what the circulation looks like. We have done several times now. Okay, and this is v dot s. Okay, so I have my v. Okay, so v is this is the integral of cosine of theta 1 plus 1 over a d theta. You know what this looks like, because this is in a vector, this is in the polar coordinates. I take the dot product, and a is a constant. So this whole thing would be 0 to 2 pi. I'm going to close the loop. A cosine of theta plus 1 d theta. This, if you evaluate this whole thing, you get this equal to pi. So last question is, could you have used the Stokes theorem? The answer is, if we think about this for a moment, I know I can use it if my loops are irreducible. Okay, if my loops are reducible, I can reduce my loop to a point. If I cannot, then it's not possible. Okay, the answer here is no, because the circulation, having a circulation different from 0, means that it implies it is an irreducible loop. Okay, so this concludes example number one.